Hello all, welcome back to my channel. Today we shall discuss on the AUTOSAR Ethernet communication stack. So like the other protocol, Ethernet also follows OSI model reference. So let's compare Ethernet versus the OSI reference model. Here the Ethernet is present in the physical as well as the data link layer of the OSI reference model, and in the application layer, we would have the application software components, and also we have in the transport layer, in the transport layer we can have either TCP or UDP, that is transmission control protocol, or user datagram protocol. Yes, of course we will discuss on this in the upcoming slides. And as Ethernet is a like internet based protocol, like in the network layer we have IP, that is internet protocol. So from the OSI model, Ethernet takes mainly four layers as a reference, like there is a transport layer where we would have the port address, network layer where we would have the IP address, data link layer where we would have the MAC address. This is how the reference is taken. Yes, so let's see how Ethernet frame looks like. But before that, whenever we speak about Ethernet, there are two types. Like one is a normal Ethernet, and other would be an automotive Ethernet. So in the normal Ethernet, like we can have like either 4 wire, 8 wire according to the speed. But in case of automotive Ethernet, we have 2 wire communication. That is that's where it stands out with the 2 wire a twisted pair 2 wire connection. And again it can have either 10 base TX there, or 100 base TX, or 1000 base TX, any one of the three. Like 10 base TX means 10 megabits per second, and 1100 megabits per second, mbps. So let's see how Ethernet frame looks like. So firstly, it will have a preamble, like it's like it's a series of zeros and ones. Like say for example, if two ECUs are communicating with each other, just to synchronize, to synchronize between two ECUs, like we have this preamble, like a series of ones and zeros, like around 7 bytes. And this would the incoming frame from one ECU to the other would be indicated by start of frame, and this would be followed by receiver MAC address or the destination MAC address, and again the source MAC address, like the sender's MAC address, followed by the type field. This type field is used to indicate like whether we are using IPv4 frame, or IPv6 frame, or like IPv4 or IPv6 protocol, or like say type. Like this information would be encoded here. Like if it is IPv4, then I think the value would be 0x800, and if it is IPv6, it would be 0x8600, something like this. The values would be there. I'm not very sure on the value, but this information would be present here. And this would be followed by the data field, mentioned, like 46 to 1500 bytes. So that information, data would be present here, and this would be followed by the padding field. So this padding, why this padding is required is that, in Ethernet, in case of Ethernet, minimum bytes that we need to transmit, like minimum we have to transmit 46 bytes. Say for example, if we do not have 46 bytes to send, say for example we have only just 23 bytes to send, then in such cases we have to pad another 23 bytes, to totally 23 plus 23, 46. This is why this padding comes handy, and so we made the padding, we add the padding bytes here, and make sure that 46 bytes are sent. And this would be followed by CRC, CRC would be added here, a checksum value. So this is our basic frame, basic MAC frame. And again we have tagged frame as well as as well in the Ethernet. Like we have the tagged frame. The only difference is that VLAN tag is something that is extra that gets added. So this VLAN tag is used to identify the packets traveling through the network links, like to which specific LAN, like LAN it is connected, or to ECU network it is a reference to. That information would be present here. It's like I think it's 12 bits value, 12 bit value, yeah, 12 bit value would, it will have a 12 bits inside this VLAN tag. 12 bits would be like used to indicate to which LAN exactly it belongs to. Whether, say for example, in your network you may have ADAS or camera radar ECU, and also you may have a body control ECU, chassis, powertrain, like that. Different network would be there. Say for example, you want to reference camera, radar, or ADAS group only, then you can provide a tag here just to just to give an indication on the MAC level, to which LAN exactly it belongs to. That information can be given here. So this was regarding how an Ethernet frame looks like. So now let's see the complete the standardized AUTOSAR architecture, like the communication flow, RX and TX, how it would look like. So say for example, an application component wants to send a signal from from one ECU to another ECU to the bus. Like if it wants to send the signal, then the flow would be something like this. Firstly, it comes out from the RT, it reaches the COM, it will be a signal that would be it would come as a signal. Then the COM converts it into IPDU, and it would reach the PDUR. So in the PDUR, like usually if it is say for example other communications, like say for example CAN or Ethernet, CAN or FlexRay, like from the PDUR usually we used to route to TP, or like CAN interface, or FlexRay interface, or FlexRay TP, CAN TP, like something like this. But in case of Ethernet, it is not possible to directly route it to Ethernet interface, because the TCP/IP stack is a socket-based socket-based communication. So the PDU based communication, or PDUR, cannot directly route it to Ethernet interface. It needs to convert it into socket based communication. So we have something called socket adapter that comes handy here. So this IPDU would be converted to socket based communication, or sockets, by using socket adapter. And below the socket adapter we can make a decision, like whether we want it to send via TCP IP or UDP IP, TCP or UDP, what we want to select. We can make a selection there based on the configurations. Then again IPv4 or IPv6, based on which IP protocol we want to send. From there it goes to the Ethernet interface and to the driver. So this is how the transmission of message would be, and the reception would be the same way upwards, like from the driver to the interface. It reaches the TCP IP stack. Then from there it would be routed to socket adapter. If it is a diagnostic message, then only it goes to DOIP. Otherwise, it will be directly going to PDUR, and from PDUR, again makes a decision. Like if it is a diagnostic message, then it goes to DCM. Otherwise, it goes to COM, and there to application. Yeah. So this would be the flow. Yes. Again, as I mentioned, let's speak about each module one by one. So let's start from socket adapter, because this is something that is something new here, because as it is a socket based communication, this is something that is extra addition here in the service layer. So as I mentioned, PDUR cannot directly route the PDU, the PDUR cannot directly route the PDU to the Ethernet interface, because TCP/IP is a socket based communication protocol. So the AUTOSAR socket adapter module is responsible to bridge this gap, and provides the functionality to map the IPDU IDs to socket connections, or socket connections to IPDUs. So that's what in the socket adapter we have this socket routes and PDU routes. So that configuration needs to be made just to make sure that we map PDU IDs to socket connections and socket connections to IPDUs. So in the socket adapter layer, here in the socket adapter layer, each of the IPDU that is coming from the PDUR, a socket header would be added. Yeah, we will be adding a socket header just to convert that IPDU to socket. Yeah, socket header will be added and will be routed downwards to the TCP/IP socket based stack. Yeah. Then talking about TCP and UDP. So let's talk about TCP now. So the transmission control protocol. So this transmission control protocol requires an established connection to transmit the data. So this is a connection oriented protocol, I can tell. This is a connection oriented protocol. Like before starting any operation, a connection needs to be opened. We need to open the connection and then start the operation. Like connection request needs to be sent first. And once we send the connection request, the other ECU responds with the acknowledgement. Only then the operation request, like whatever operation we want to carry out, that operation can be sent, and then the response would be given back. Operation request and the response, and at the end we need to make sure that we close the connection. So that's where in the TCP/IP it takes little more time to when compared to UDP. But it guarantees the delivery of the data to the destination, and also retransmission of the lost packets is possible. At least retransmission would be possible, and there is a extensive error checking and acknowledgement of data is present. That is one good thing here. And as I already mentioned, connection should be closed. The closing connection, connection should be closed once the transmission is complete. And this TCP is a unicast communication. Yeah. So now talking about UDP is a connectionless protocol with no requirement for opening the connection or maintaining the connection or closing the connection. So there is nothing like no connection request and acknowledgement or closing connection. Those things are not there. Directly operation request and the response. Operation request response. Whatever operation you want to carry out, operation request response. So it's like that. And also it cannot guarantee the delivery of the data to the destination. Also there is no retransmission of the lost packets. So the basic error checking mechanism is present here using checksum CRC, and it is a unicast, broadcast as well as a multicast. But only thing is like it cannot guarantee the delivery of the data, and also no retransmission is present. So that is the main difference between UDP and TCP. So based on our requirement we can choose which we want. Usually like in the DOIP, like the vehicle announcement thing, this happens through UDP. Later on the routing activation and then the transmission of the diagnostics, those things for that we use the TCP thing. Yeah, so based on the need we can make this selection. Then after this we have this IP. IPv4, like in the IP internet protocol there are like two types. One is IPv4 and IPv6. Just to take as an example, in the IPv4, the address would be something like 192.168.0.1. But the question would be, why did we move from IPv4 to IPv6? So the main reason was, like in the IPv4 we were out of IPs. That's the reason we moved to IPv6, which has 128 bits of address. So there are lots of IPs that we can make use of. So this internet protocol is used to send and receive the data as packets across the network through routers. Each packet has associated source and destination IP address. This is where the IP address gets assigned. And IP address are specific to a node or ECU which uses the IP protocol for communication over the network. So this was regarding IPv4 and IPv6. So also in the DOIP for the diagnostics, like we make this we use this DOIP where we configure all the diagnostic related information, like the DOIP diagnostic channels, the tester source address, the buffer size, the routing activation part and target address and DOIP connections, all the connections needs to be configured here. Then from here PDOR as usual, like it has a routing table based on which like it will route to the from source, from which like from source to the destination it will just route it. And also the gatewaying is also possible, signal level or PDU level gatewaying is also possible. Then the COM layer, like mainly the signal to PDU conversion, and the timeout, a lot of other things can be handled, but main thing is like the conversion. Yeah. And in the DCM, like processing the diagnostic request would be carried out at the DCM in the 3 layers: DSL, DSD and DSP. So this was regarding almost all the modules that we have in the Ethernet communication stack. Now let's see again, like from the driver level, like each model, like the minimal configurations as well. Yeah, but before that, yeah, we have something called MMII, media independent interface. Like you have this physical layer as well as the MAC layer here, right? Physical layer and the MAC layer. So using this media independent interface we can connect them, like yeah, we can interface the physical and the MAC layer. Like as we already know, the main difference between the normal and the automotive Ethernet is that the physical layer. So in the automotive Ethernet we may have either again it may have either 100 base, 1000 base, or 10 base TX. So even though we change this physical layer, media independent interface will make sure that the transmission is happening smoothly between the MAC and the physical layer without any interruption. Yeah. So this media independent interface is a standard used to connect the MAC and the physical layer. So that is one thing we need to configure this at the driver level, Ethernet driver level. Yeah. So yeah, this is done. And yeah, the flow is also explained, like the transmission and the reception, like how the flow would happen. And one more thing was like, yeah, this frame I just wanted to show. So in the Ethernet frame, if we speak about, it will have a source and destination MAC address and the IP datagram. IP datagram would be present, Ethernet frame. Then if we speak about IP datagram, again it will have the source and destination IP address, followed by the TCP segment would be present. And if we speak about this TCP segment, it would have the source and destination port address, followed by the IPDU, which is again routed to the PDUR. From socket adapter it will go to PDUR, and from PDUR it goes to the COM. Again it gets signal level and again access to the application. That's how it would be. So if it is a transmission, then one by one this addition would happen. Like it gets added, like first the source and destination port address, then the IP address addition, then the MAC address addition, and going out of the ECU. If it is reception, then one by one it will be removed, and then finally it reaches the application. So the same thing, like with respect to OSI reference model, it will be easy to understand. So here in the data link layer you would have the MAC, in the network layer you would have the IP, in the transport layer you would have the port address. That's what. Yeah. Then as I mentioned, let's see each layer one by one. Say for example, what are the basic things that we configure in the driver level? So you may have this, it's better that you know this, as usual, like as other drivers, like usually the clock reference we will be providing, that configuration needs to be taken care. And as I already mentioned, in the Ethernet we have this media independent interface, just to interface between the physical layer and the physical layer and the MAC layer. So to interface that, we need to select what kind of media independent interface. Like there are three or four types, like RGMMI, like there are 3 or 4 types. Based on our need, we need to select that. And the MAC address also is configured here in the driver level, like it's a 6 octet that we need to configure here for the Ethernet driver, Ethernet hardware. Then the port speed selection, like whether we want 100 Mbps, 1000, 10, like that needs to be configured. And the receiver buffer size also needs to be configured here, and the Ethernet driver, like the register base address of the Ethernet controller. Yeah, the register base address of the Ethernet controller needs to be configured here. So this is something the like Ethernet driver basic configurations. Then talking about Ethernet transceiver configuration, as I already mentioned, Ethernet transceiver is used to control the transmission and reception of the Ethernet frames, like the states of the Ethernet physical, like whether it is busy or free, that will be controlled by Ethernet Ethernet transceiver. So here again, the speed of the Ethernet transceiver link in megabits per second. Then the controller, like Ethernet driver controller reference, we need to provide. Then again, the media independent interface selection needs to be done. So these are some basic configurations that we make in the transceiver and in the Ethernet interface. Yeah. So in the Ethernet interface, again the controller and the transceiver reference needs to be provided first. This should be followed by like the VLAN ID, like VLAN ID configuration, like 12 bits value we need to provide here, which I discussed. Say for example, for few of the for the Ethernet frame on the MAC level, if we want to inform to which VLAN specifically it belongs, to which ECU or which ECU network it specifically belongs, then that ID can be configured here. 12 bits value needs to be configured here. And also in the Ethernet interface, we configure the maximum transmission units, which is the maximum frame size that can be transmitted on the network that needs to be configured in the Ethernet interface. And RX indication configs and TX confirmation configs needs to be done. And again, in the Ethernet driver or interface or transceiver, the main function, the timing information as usual needs to be configured. Yeah. So these are some of the basic configurations that we do in the communication driver and communication hardware abstraction level. Then on the TCP/IP level, the TCP/IP stack level configurations would be the IP configuration. Mainly, the IP configuration needs to be done. Then, TCP/IP, ARP, DHCP, and ICMP protocol configurations needs to be done if ever it is needed. Then, the socket buffer size, TX and RX buffer size, and main function time period. So these are some of the basic configuration. Mainly the IP will be configured here, and the socket buffers size and ARP, DHCP, and ICMP protocol information can be configured here. Yeah. Then in the socket adapter, so in the socket adapter, as usual, like socket to PDU and PDU to socket. So the socket routes and PDU routes needs to be configured, where we would map from which socket to which PDU and which PDU to which socket, like vice versa. That needs to be configured, and socket adapter routing groups and the connection groups needs to be configured. So this is the main configurations in the socket adapter. Then DOIP. So this is something related to diagnostics. Of course we will make another video for this DOIP, but to tell on this roughly, in the DOIP specific interface, the DOIP channels needs to be configured. In the DOIP channels, like mainly the source and the source address and the tester address, the ECU and the tester address needs to be mentioned, and the maximum buffer or the PDU size, RX and TX PDU reference, and routing activation, which would have the target address, DOIP tester, where the tester address and the routing activation reference, and the DOIP connections, like mainly the vehicle announcement connection, UDP connection, TCP connections, and IP address assignments and the target address. All those information needs to be configured here in the DOIP. And above in the PDU router, like it will have a routing table where the source and destination, that information will be present. And in the DCM, as usual, all the DSL, DSG, and DSP, like the page like the buffer size information and paging information, or the DID, RID, PID, all these related diagnostic configurations needs to be done, and service table configuration, all those things would be done there. And in the COM layer, like IPDU, signal groups, IPDU groups, all those things needs to be present. From the ECU extract it will come directly, so those things needs to be configured. This was roughly on the configurations of each modules. And hope I think I have covered everything, and so nothing is left. So so this was regarding the Ethernet communication stack on AutoSAR. So thanks for watching the video. If you like this video, please give it a thumbs up. Yeah, thank you.